There we go.
Are we going to finish the other 2 slides on the PowerPoint?
Yeah,
Okay.
they come after this.
Okay.
Yep. So once we go through this mechanism, then we talk about the oxyanion hole as my transition state stabilization. Don't worry, I'm very excited to get to those too. All right, serine protease mechanism. I'm going to draw it in 5 steps. So kind of space yourself out. Have 5 steps. All right, so that's going to be my active site. This would be a great opportunity to color code if you have multiple colors with you today. All right, here's my active site with my aspartate that they talked about, the histidine, and the serine. Entering into this is going to be our peptide. All right, so there's our peptide bond between the amine and the carboxylic acid, peptide bond right there. And serine proteases, I don't know if you caught that in the video. Their job is to break peptide bonds. And so break multiple, a long chain protein and just kind of cut up some of the pieces of it. Okay. So the first thing that's going to happen, bless you, is that histidine is going to interact with the serine. So this alcohol, right, this terminal OH, not a great nucleophile. I'm going to put little notes underneath each one of these. So serine in its native state is not going to be a strong nucleophile. But histidine's going to act like a base catalysis. And this nitrogen is going to abstract that proton from the serine. How does that leave that serine? What charge does it have on it? Oh, no. Negative. Right, if we abstract a proton, then we are left with extra, this will be now O- over here. So serine was not a strong nucleophile, but now we have a base catalysis. So that is histidine is taking that proton. It's going to leave our serine as an O-, which now is a killer nucleophile. And that is now able to attack the protein or the peptide chain. So really, there's 2 types of catalysis going on here. Histidine acted like a base catalyst because it took a proton to leave a base. So then serine is now able to do covalent catalysis and make a new bond between itself and this peptide. All right, so now we have step 2, where we now have this new covalent bond that has been formed between this oxygen and that carbon. Here, am I see what I'm writing? That's a single bond. Sorry. Should be a single bond. It's a real thick single bond. We have now formed our tetrahedral intermediate. Which is as the video said, we could either, at this stage, return back to our original or finish the reaction. Because of the amino acids that are in here, we're going to be able to finish the reaction. So this histidine and this proton are having an interaction that we'll get to in a minute about the oxyanion hole. But know that these two, O- and this proton, are pretty much acting ionically, that they are being held together fairly strongly. This O- in this tetrahedral intermediate is going to collapse. Then going to push electrons onto this nitrogen, which will then abstract that proton. So over here, histidine was acting as a base catalyst, where it was taking a proton. Over here, it's receiving a proton, so it's now acting as a acid catalyst.
You said it's receiving a proton, right?
This guy is going to, the peptide is going to get protonated to become a better leaving group. So this nitrogen, the nitrogen in the peptide, becomes protonated, so it will become a better leaving group. Good on that step. Step 2. So now we've broken this bond. This bond right here has been broken, which means we are going to eliminate this NH2R2, because this bond has been cleaved. So now we have to regenerate the enzyme, because, right, it's done its mechanism, but now we've get back to the point where the enzyme is regenerated. The first thing we're going to do is we're going to add some water to our active site. All right, so that's where we're at now. Once that left, we have go. So now I'm going to add some water to my active site. Bless you. So one of the things the water is going to be able to do is going to enter the active site and it's going to donate protons to histidine. So in the remaining hydroxyl group, right, the part that's left from the water, the OH minus, it's going to attack the carbonyl group of remaining peptide. So when that happens, we push our electrons back up on the oxygen. All right, because we are trying to get to the point where we've cleaved off this part. So we're going to have to make it a better leaving group than what it is right now. So what we're going to do is we're going to pretty much do the exact same step that we saw in the first place. All right, the very first step we saw was histidine abstracting a proton and then this oxygen attacking a carbonyl. We are now looking at histidine abstracting a proton and oxygen attacking a carbonyl. So step 1 and 3 are pretty much the same steps. It's just what carbonyl it's working on. Know that there's like arrow, and I'll start drawing down here. All right, so this is what we get after that, right? We have protonated our histidine. That carbonyl now has this extra alcohol group on it, but then it's single bond O minus. It looks crazy. I keep trying to draw a double bond. It's wrong. Single bond. Both times I've done it. What do we now see here that we saw over here in step 2? We have now another tetrahedral intermediate. which again is another stopping point that we could either go back to step 3 or continue on to step 5. What we see happen is this collapses down onto that carbonyl carbon. We then regenerate our histidine, and we cleave this bond. And as we saw in step 2, histidine is again acting as an acid catalyst. So histidine acts like a base catalyst, then an acid catalyst, then a base catalyst, then an acid catalyst. So it flip-flops between what it's able to do. So base, acid, base, acid.
The middle arrow that you have drawn here? Yes.
Yep.
Are the electrons from the oxygen going to the hydrogen, or are you forming a bond there, or is that?
Yes, it is making a new bond.
Okay.
Yep. So yeah, in that way, serine's acting as a covalent catalyst because it is making a new bond. We'll put that down here. It's going to form a new bond to get back to our original So this guy up here has broken off. So we're eliminating this fragment of the peptide. And we're back to where we started. Yeah.
Is right above the arrow, is that supposed to be a double bond for the O? Like when you're moving to the next step? Well, yeah.
Yeah, double bond oxygen. Yep, yep. So, yeah, John.
About how long does this process typically take?
Excellent question. It takes less than a second. So it's able to do all this chemistry really, really quickly. If you think about it, that's just one enzyme, just doing its job, just cutting up proteins. And you got all these enzymes in your body doing this all the time. Able to do all these organic reactions quickly and correctly every time. So, fun facts. So, the catalytic triad that they mentioned in the video is the aspartic acid, the histidine, and a serine. You can go in and you can do like 1 amino acid changes in active sites. It takes a little bit of work, but you can do it. And so they've done experiments to figure out, well, how important is it to have this particular combination of enzyme, of amino acids in the active site? When they replaced serine with glycine, something that's not able to do any chemistry in this way, it reduced the ability of this enzyme to work correctly by over 1,000,000%. So pretty much it didn't work. Didn't work anymore. So that's why these are called serine proteases, because really it's the serine that's able to do most of the chemistry. When they went in, they replaced either the aspartic acid or the histidine with compounds that either weren't able to do acid-base catalysis or weren't able to have a full-on negative charge at that pH. %5,000 reduction in the ability of this enzyme to work correctly. So that's why you can see that serine is going to be the most important, but you also need the two other amino acids that, especially the histidine, that can do the acid-base catalysis over and over and over again. Yes?
So why wouldn't something else that can do acid-base catalysis? Like, were there 6 that could do those?
Right. This is when they replaced it with like a glycine again, or something that wasn't able to do, right, wasn't as fast. So probably there's some combinations that you could put in there that would be able to do it, but if you flat out took them out, then they weren't able to.
Never mind, you just did.
Oh, okay. So, oh yeah, this way, that way?
Down a little bit. Yeah, there you go.
So, the other part of the video that you may not have seen because it was kind of a weird spot, it was down off to the right. I'm trying to picture which way it was. On the right was our transition state stabilization graph, which is the next PowerPoint if you have that. If not, we can all sketch it together. So, let me get to my right page of notes. Transition state stabilization is the idea. That's still really tiny, isn't it? It's the idea that you bind the transition state of the reaction that catalyzes with greater affinity than you would bind the substrate or the end product. So, there we go. So we bind the transition state of the reaction catalyzes with greater affinity than either the substrate or the product. And why biochemists think this is that the rate enhancement of a reaction by enzymes is often greater than can be accounted for by just looking at the substrate and product. So either the enzyme substrate or the enzyme product. If you just look at the chemistry of what's going on there, it shouldn't work as well as it does. And it's because, really, there is a transition state that binds really, really well. So if we're looking at the transition state reaction coordinate for this reaction, so this is what we drew before, right? We had enzyme plus substrate goes through some sort of transition phase, this S double dagger, and then we end up with enzyme plus product, right? So my green line is this reaction. Which is what we have been discussing this whole time, that E plus S goes through a substrate transition, which then we get E plus P. Great. That seems to work real well. But in reality, what they see is this. That there's actually multiple intermediates. That's actually that we start as the enzyme plus substrate, which then makes some sort of covalent combo, an ES combo, which then goes through a transition state, ES transition state, which then makes the enzyme product covalent combination, which then you get your original enzyme back plus your final product. Which is kind of what we saw at the serine protease, that we had this part, the first step, where there's a covalent bond made between the serine and the peptide, which then went through the tetrahedral intermediate. So there was an intermediate where part of the peptide had left, but the other part was still in there. So then we had to get through our final product where they break apart again.
Did you say that the red is what actually?
Yes, yeah. The red is more correct. So right, delta G transition state is the measurement from your starting materials to the transition state, right, which is different than delta G regular. Right, the double dagger tells you the activation energy. So the activation energy of the native enzyme, as we imagine it, would be higher. Because what we actually see is that the transition state energy is much, much lower. Because we're only actually going up to that activation energy, because we've forced it through a different step. So that delta G transition state for the enzyme is a much lower transition state energy than you would expect if you were just drawing yourself out a reaction coordinate diagram.
And delta G, we double dagger is the transition.
It's the energy between your starting material and your transition state. So activation energy would be another good word for that. Questions on that? Yeah, Rachel.
So, is this graph basically telling us that it takes less energy than expected to produce a product?
Yes. Yep. that going through this multiple transition state is actually even more efficient than it should be. Okay, in that case, let's look at the last thing with enzymes, which is catalyst through proximity and orientation. Okay, so catalysis through proximity or orientation effects is really two parts. One, you're going to bring the reactants close in proximity. Physically, they will be close together. As you remember from like a bunch of other classes, the closer the things are together, the more likely they are to react. That should intuitively make sense. And then the binding of the substrate to the enzyme causes a conformational shift in the enzyme. So we're going to look at hexokinase as the example for this because it has the most dramatic conformational shift. We'll come back to this enzyme in a few weeks when we start talking about glycolysis. But here's what it does, and then we'll look at how it does it. Make sure there's no space. Bless you. Okay, there's my molecule of glucose. What hexokinase does is it phosphorylates the 6th position of glucose. So what you end up with is after hexokinase has reacted on glucose. Not good at drawing 6-membered rings. So glucose has become phosphorylated at that 6th position to glucose 6-phosphate. That's what it makes. It leaves behind some ADP. So the more interesting part is how hexokinase does this reaction. Turns out that hexokinase has 2 hinged lobes. Now I'm going to draw a very cartoonish picture. There's a much better diagram in your book. Looks something like that. Not really. But here's my glucose. Here's my ATP. They're going to enter the active site. and hexokinase clamshells around them. They do like this. Not quite that fast. Right. So hexokinase places the glucose near ATP, which would be our proximity. They are in close proximity to each other. And then the two hinge lobes close to prevent water from entering the active site. Now you'd be thinking, that doesn't make any sense because it seems like water is very important to all these reactions. It's because, write this over here. ATP can be hydrolyzed, and so we have a competitive reaction. So if water enters the active site, ATP will react with the water rather than the glucose. So the hexokinase has to close to prevent water from getting in there and making any side reactions. Which way?
So the whole next one.
That's everybody. So the closing of the two lobes does two things. One, it prevents water from entering the active site, making any kind of side reactions. And the other thing that closing the two lobes is able to do is that it enhances reaction by lowering the delta G native state of the enzyme. So by putting them in close proximity or close orientation, it goes through the transition state that we just saw over here, where it would have been just this, but now because of this, it makes it ES transition state, which enhances the rate of the reaction, lowers the activation energy. How'd that go? Pretty good? Yeah. Excellent. So you may be thinking, how am I going to test you on that? Excellent question. I could either ask you questions about the specific serine protease reactions, or I could ask you to draw a step, like draw me step 3 of what's going on there, or in words describe. It's the only reaction I'm going to have you have to like really, really know for this next little test coming up. It's only the group quiz on Friday. It'll just be about what we do. I guess not. I won't have you draw it for Friday. No. For Friday, it'll just be like, how is histidine acting? It can be an acid or a base catalyst. Or how is serine acting? It is a covalent catalyst.
So this is the only one that we really need to
For this test. Yeah, this is the only reaction we're going to look at in this section. Yeah. All right.
So you can